All right, I think Dan is just going to kick it off.
All right. Yeah. Hi, I'm Dan Roy. I'm assistant professor in statistics at the University of Toronto, though I was trained as a computer scientist, and it was at MIT that I worked with Akash and Noah and Keith and Josh and introduced the church programming, probabilistic programming language. After that work, I started thinking about the foundations of probabilistic programming, in particular the limitations of computing conditional distributions when the distributions are presented as programs, and I got very interested in symmetries and how they give rise to conditional independencies. And so what I'm going to be talking about today is sort of the synthesis of some of that work and some more recent stuff. So this is about algorithmic barriers to representing conditional independence. So independence, so just a quick review and also set some notation. So I'll write P of A here to mean the probability of some event, maybe talking about some random variables or whatnot. And a family of random variables is independent when the probabilities of these random variables falling in different sets factorizes in this way. So this joint event, the probability of this joint event becomes a product of the individual events. Now if I use this notation here, P, Y in C dot, I'll use this to denote a distribution. Then I'll write one in a more compact style like this to say that the joint distribution is a product of the marginals. Now, what's the use of this computationally? Well, this is well appreciated if I have these n, say, binary random variables to make this simple. Then in general, this joint distribution I need to determine it. I need to specify 2 to the n minus 1 numbers. And for a long time, I think people who were, say, against probability in AI viewed this as a major impediment to dealing with probability, or using probability to manage uncertainty. Now, if there's independence, this complexity drops dramatically, and you only need to specify n probabilities. You need to specify the probability that each one of these individual random variables on its own takes the value 1, for example. Now, conditional events. Actually, going back. So independence is a very strong assumption, and it's rarely present in an interesting model. On the other hand, conditional independence is rife, and it's a major modeling idiom. And it's just kind of one level more sophisticated than independent. So I'll write P of A bar X to denote conditional probability of an event A given a random variable, right? That variable taking values in some space S. And now a family of random variables is conditionally independent given that random variable X when, again, I have this joint event, this conditional probability of this joint event factorizing into the product of these individual conditional probabilities for each one of the variables on its own. Again, introduce notation for the conditional distribution of a random variable, and I can summarize that formula above here by this this joint conditional distribution being able to be represented as a product of kind of marginal conditionals, if you will, though I've never used that word before. All right, so and in the same way, we get a more compact representation of this collection, though conditional independence is much more useful because because they're allowed to be dependent. So in general, this joint distribution condition on X requires a specification of 2 to the n minus 1 functions from S, the space that X lives into probabilities. Whereas if I have conditional independence, I'm only specifying n of these functions, right? And probabilistic programming is in some sense leaning very, very heavily on conditional independence the program structure itself in some sense exposes the conditional independent structure of the underlying random variables. All right, so I'm very interested in the relationship between conditional independence and computational hardness. And to take a step in that direction, talk a bit more formally, we can formalize what it means to, say, represent a conditional independence, and I'll just do a very natural thing, which is to say that the conditional independence of a family, say y1 through yn, given a variable x, I'll say that's represented by the conditional distributions, the individual distributions for each element of that family. And then I can talk about these conditional independencies being, say, computable or efficiently computable, which I'm not going to attempt to formalize that in 20 minutes. All right, but now we can talk about, say, the relationship between the computational hardness of joint distributions and their conditional independencies. that they possess. So worthwhile thing to point out is that conditional independence underlies efficient computation. And the basic connection here is obtained by the connection between efficient computation and the existence of circuits of small size. So let's consider that for say every natural n, you can efficiently generate from some family of random variables, y1 through yn. Now in general, this collection of random variables, despite being efficiently sampleable or generatable, need not possess any conditional independence. So there need not be any apparent conditional independence among these random variables. This factorization that I've written here is one that always exists. This is basically an axiom of probability, and this is a trivial Bayesian graphical model Bayesian network, and I'll talk about Bayesian networks in a moment. However, there's a polynomial p, and there exists a polynomial number Pn of binary latent variables z1 through zpn, such that there is a very sparse constant fan Bayesian network involving this large collection of random variables, whose conditional distributions are then very efficient. So I just have to kind of step back and introduce additional structure, and now this conditional independence is apparent. All right, so conditional independence and efficiency is very closely connected. So Bayesian networks encode conditional independence. A major revolution in AI was noticing that by exposing the conditional independent structure of a collection of random variables as a graph, and then using graph theoretic algorithms, you could come up with very efficient algorithms to perform probabilistic inference, aka computing conditional distributions. So the graph here structure communicates a number of independencies and conditional independencies. For example, I can read off from this that I know that difficulty and intelligence are independent. I know that difficulty is independent of the letter grade. The difficulty exam is independent of the letter grade once I know what grade you got, because the grade just kind of begets coarsening the letter grade. Now, this graphical model this distribution over this collection of 5 random variables corresponds to a probabilistic program. And indeed, the structure here is apparent in the structure of this code. And so one question you might ask is, if I have some family of random variables, and I can say efficiently generate this collection of random variables, and they moreover satisfy some conditional independence structure like a Bayesian network, is it necessarily the case that a presentation of this distribution that reflects that structure is efficiently computable. So that's another way of saying, if I have this joint distribution and a family of conditional independencies that hold, are the conditional independencies themselves computable, efficiently computable, say? Well, that's not the case, because basically you can turn this into an inference thing. It has to do with the fact that if I have a Markov chain, I can reverse the arrows. So let's say I have 3 random variables, eta, theta, and x, eta being independent of the other 2. Then I obtain this factorization, which is basically 2 different Markov chains that these random variables happen to satisfy. And what's possible is it's possible to find pairs theta and x. Eta doesn't really matter here because it's independent. It's possible to find pairs theta x such that x condition on theta is efficient, and indeed that's, I've chosen these variable names because that's sort of meant to conjure up the idea of a likelihood that you might specify in a generative model. So this might be efficient, but then in the reverse direction is intractable. Easiest way to construct these things is to assume, say, the existence of one-way function, think like a hash function. I generate a random length n string, and I hand you the hash, and then you're challenged to figure out from the hash what my string was. That's the hard direction. But generating the hash is trivial. It's a bit worse than that, actually. So it's possible to find pairs if I if I allow myself to have a continuous random variable x. It's possible to find pairs where this forward direction is computable, but the reverse direction is not computable. And that's related to some work that I did with colleagues that I showed pictures of at the front, but I didn't name them. So that's like some work with Nate Ackerman, Cameron Freer. So conditional independencies may be computationally harder than the joint distributions that they relate to. A setting where there's settings that's rife with conditional independence is the setting of exchangeable random variables. So this is, these are collection of random variables that satisfy probabilistic symmetries, and due to this, there are powerful theorems that tell you that they must then possess certain conditional independencies, and actually more than that. So it's interesting to consider, and these types of exchangeable structures appear a lot in statistics, and so it's an interesting question whether you can represent these computationally. Can you build, say, in the language of probabilistic programming languages, can I have the structure of my probabilistic program mirror the conditional independence structure that I know to exist mathematically? All right, so let me explain exchangeability. This is the math definition. I'll give you a more concrete example on the next slide. So I have a sequence of random variables. It's going to be important that it's an infinite sequence, which don't think about that as some sort of weird math thing. That's more like I can run the program longer and longer and longer and generate on any, there's no bound on how many elements of the sequence I can produce, right? That's really what's going on here. It's not that it's some kind of mythical infinite sequence. So I have the sequence of unbounded length, infinite. And it's exchangeable when, say, for all n, the initial sequence is equal in distribution to any permutation of that initial sequence. So the order of the sequence doesn't affect its distribution. If I were to generate the sequence and then when you're not looking, swap two of the elements, you would never be able to notice by looking at the distributional properties or statistical properties of that sequence. And this has to hold for all n and all permutations. And the theorem of Dependencies is the following, that a sequence, an infinite sequence like this is exchangeable if and only if it is conditionally independent and identically distributed, which in the notation that I've been setting can be expressed like this: for some random variable, and this random variable can take various forms without loss of generality, but for some random variable, say theta, the conditional distribution of the collection given this random variable factorizes. That's conditional independence. And then the conditional identically distributed aspect is that, moreover, the distribution of any condition on theta, the distribution of any one element is the same as, say, the 42nd, or the first, or the third. Okay. So to specify the law of this sequence, I really need only specify the distribution of this random variable and this one conditional distribution, right? So things simplify considerably. And one question you could ask is, what is the relationship between, say, the distribution of the sequence itself and this structure here? Are they on the same footing computationally? So to give you a bit more, experience thinking about exchangeability, so here's a program, probabilistic program in a fake language, that here's a procedure, next draw. Every time you call it, it's going to return this variable y, and this variable y is going to be either it's coming from Bernoulli, so it's a 0 or 1. So I might see a sequence like this. So this repeat procedure apparently calls next draw 10 times and puts it into a list. Now, if you run it, you might observe a sequence like this. So it moves to the right every single time. It gets a 0 and moves up when it gets a 1. And so actually this pattern here is exactly reflecting this pattern here. If I ran this program again, I might see this pattern. And what's an interesting property of this particular program is that the probability of seeing this path and this path are identical because they land at the exact same point, which is to say that the probability of seeing a particular string of zeros and ones depends only on the number of zeros and ones, which, if you think about it a little bit later on your own time, is going to tell you that this sequence of random variables is exchangeable. Now, if you run this red one out, you'll get this line. If you run that blue one out, you get a slightly different line, but indeed, something interesting going on here. It's converging to a line. And what's going on is that line encodes a probability, and it's actually reflecting the fact that this program on the left is equivalent to this program on the right, which is one where you all at once choose a random variable in the unit interval, and then every time you call this procedure, rather than there being some mutation that occurs and updates, there's no mutation whatsoever. You're just always flipping this one variable. So if you were to take this program and remove this variable and deal with the updates using mutation, you would get this program. All right, so marginalizing out a variable gets you this type of exchangeable mutation, which I've studied with Nate and Cameron and also Sam Staten and Han-Suk Young. Perfect, yeah. All right, so that's exchangeability. Hopefully you have a deeper feel for it. So this theorem of Definetti tells us when we have this exchangeability, there is this conditional independence and identically distributed. So exchangeability is the fact that the distribution, the outputs of this procedure are invariant to reordering, and this is kind of the structure of this program is kind of witness to the fact that it is a conditionally independent and identically distributed distribution, conditionally ID sequence. Now, a third way to express this equivalence is that there exists a measurable function f such that the distribution of this sequence of random variables is the same as you would obtain by repeatedly calling this function f. Every time you call it, you pass it the same first input, theta, 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 and you pass it a fresh second input, u1, u2, u3. These can be taken without loss of generality to be IID uniform. And what's going on here is that this is a reflection of the conditional independence structure in yet another way. This sequence is apparently conditionally independent and identically distributed once I give you theta. Because these are independent of each other, and they have the same law, and so condition on theta, these have the same distribution as well. So this manifests, and in some ways this is a rather effective way to present this notion of conditional independence and identical distribution, because this f is, if I could implement it, would be something like a sampler. Indeed, so in one of the first pieces of work that I did with, say, Cameron, thinking about computability and probabilistic programs and exchangeability, was this theorem, which is that if you have a exchangeable sequence, then the following equivalent, the joint distribution of this exchangeable sequence is computable exactly when some f satisfying this equality is computable on a measure one set. And in fact, this relationship is uniform in the sense that from a description of the joint distribution, we can extract a description of a function f. So that's about computability. I'll return in a moment to the complexity. So we can move automatically from this presentation to this presentation. So just briefly, so I just been talking about extracting conditional independencies from sequences. You can ask the same question, hey, how about arrays? Like, for example, I could have an array of random variables that's jointly exchangeable in the sense that I can like swap rows and columns. It's a different notion of different probabilistic symmetry. It gives rise to there's a different representation theorem here. It's not Definetti's, it's Aldous Hoover. And again, there's this function f lurking underneath the surface. Unfortunately, in more recent work, we show that there exists exchangeable arrays, random variables that are computable. I didn't say that. There exists computable exchangeable arrays such that no f satisfying this identity here is computable. So the conditional independencies lurking under this array are out of touch, or you cannot represent them computationally, unlike the array, sequence case. In some special cases, you can get at it kind of arbitrarily close. You can kind of compute it with arbitrarily high probability, which I think is an interesting line to pursue. So I don't have time to go through this, but if you start asking about what's the complexity of conditional independence, you have to, much more so than in computability when almost all ways of representing distributions are equivalent, complexity, they are quite different. Being able to compute cumulative distribution functions is different from pointwise probability mass functions, is different from efficiently sampling, is different from sampling up to indistinguishability in the sense of cryptography. I'm going to skip over this. You might ask, so I mentioned the complexity of the computability of the Definetti theorem. You can ask the complexity question. A very nice kind of simple version of this question was posted by one of my thesis committee members, Scott Aronson. So he distills it down to this. Do there exist probability distributions D1 and D2 over n-bit strings such that D1 squared plus D2 squared over 2, which is the equal mixture of two independent samples, either from D1 or D2 with equal probability, is efficiently sampleable, even though neither of them on their own is efficiently sampleable. It's sort of this, it seems like it should not be possible, but it's sort of like you can bang your head up against it. I have what, minute, minus minute, 1 minute, so I'm going to skip this. It's just kind of an interesting fact that if you're familiar with Bayesian nonparametrics, there's something called Pittman-Yor. You can generate a Pittman-Yor sequence of length n in quadratic time, but if you study the stick breaking construction, then the moment the discount parameter gets bigger than 1/2, it takes infinite time in an expectation, which is sort of a big dichotomy in terms of complexity of the conditional independence versus the sequence itself. But I'll just pause here to explain this very quickly. So this is a special case. So now we're going back to the Scott's case, but we're giving ourselves a bit more. We're not saying you only get 2 samples. Now I get as many samples from D1 and D2 as I like. So I have D1 and D2. They're measures on 0, 1. I'm going to pick one of them at random. K is going to be a random choice of which one. I'm going to condition on K. I'm going to get a bunch of samples from DK. And I don't get to know which one it is. And then there's this interesting fact that I can produce this function f. It's going to receive as input. So here's my sequence y1, y2, y3. This is this exchangeable sequence. And actually, the sequence of this y is equal in distribution to f, this particular f up here, applied to y itself in u1, y itself in u2. So I'm actually using the exchangeable sequence itself as its own kind of latent variable. And what I'm going to do with this sequence is I'm going to compute the limiting relative frequency of ones, and I'm going to compare a uniformly distributed random variable to that. That satisfies this law, and so this f here is indeed one of these nice representing functions. And while this thing is not computable, this is a discontinuous everywhere function. It's not going to be computable. It's discontinuous on every measure one set as well. So this thing is horribly non-computable, but it is nicely computably measurable in a sense you can formalize. And indeed, for every delta in the unit interval, there's a computable function f prime, so different from f, that runs an expected time order of log 1 over delta and agrees with f outside of a measure of 1 over delta. So you can get kind of tantalizingly close to finding a representative of f that is accurate. You just can't do it perfectly. And so the question is, like, can I do this with delta equal to 0? I have no clue. And you can do this for any, say, finite set of distributions, but once you go to countable or have a limit point or just have a general, something called definite measure, then I don't know. So that's interesting. All right, so in conclusion, conditional independence is intimately linked to efficiency in distributions. Conditional independencies need not yield efficient representations, and I argued this via reductions to inference. Focusing on the setting where there's probabilistic symmetries, conditional independence underlying exchangeable sequences can be extracted computably. We don't know yet whether it can be extracted efficiently or whether even non-uniformly it can be represented efficiently. In arrays, it can be inaccessible. All right, thank you.
So we are running a little bit over, but we'll take a quick question if somebody has one.
Yeah.
Yeah? Oh.
Could you maybe give a brief intuition for why the computable connectors are false, but when you apply that to the Albert-Huber case, there's no analysis result?
Or repeat the question.
Yeah, so I'll repeat the question. So basically looking for some intuition why the one-dimensional case is computable and the two-dimensional case is not. So I'll zoom back here. I'll make it quick. Don't worry about it. See this function here? Once I fix this first variable here, what you notice is that this function f is very ill-defined. There's many f's that work, right? If I were to say define an f where I take this input and I take 1 minus that input, I also get a function that satisfies this. There's many functions, and they're kind of equivalent up to a measure of preserving transformation. But in the case of one dimension, which this is, there's a canonical choice, namely the distribution function. There's no canonical choice in the array case. And that's and the obstruction is a topological one.
All right. No. All right, let's thank our speaker again.